Okay, so 15.3 uses of electromagnets. First of all, I'm going to tell you what I didn't tell you in the last lesson, which was about the second way of telling what the pole on a solenoid was. So just to recap, the first method I told you was the devil's tail rule. So if your current is going this way, like so, then you know that that's a south pole. Okay, but that can be a bit confusing. It's not always the most obvious. That's the devil's tail rule. So the other method, which I didn't tell you about, was that if you have a solenoid where that's your current, and you can see it's going to go like this. Okay, well, you know how I told you about the right hand grip rule for if you want to know which way the field's going, so when you know the current, so if the current is going that way towards my thumb, then I know that the field will be going in the direction of my fingers. Okay, that was the right hand grip rule. Well, the reason why the right hand grip rule works is because the current and the field, the magnetic field, they're always at right angles to each other, and that's the crucial rule. Which means that, well, if you said that this bit here, the coil bit, was your fingers, then your thumb, so if you grip, right hand grip rule this way, what you can say now is, if I grip it like that, so I can see that the coils are going that way, so my arrows are going the same way as my fingers, then my thumb points north. And all you're doing is just saying this in a different way. So you're just saying, because the current is always at right angles to the field, you can apply your right hand grip rule. You can either grab hold of the bar, or you can grab hold of the wire. Now if you grab hold of the bar inside a solenoid, so let's say that there's a bar inside here, because it's easier to visualise, just to make the field strength stronger, like we said last lesson. And you grip that bar, and you feel your fingers are the current, well then your thumb points north. But if it's a wire and you grip it, then it tells you which way the current and the field are that way. Okay, so you can use it two ways, it's quite handy. Okay, so the uses. Well, the first use is if we go for a normal circuit, and in this circuit what I'm going to have is I'm going to have an electromagnet and then there's going to be an arm here, a contact, a pivot. Okay, there's going to be a pivot, and there's going to be a bell here. Okay, so before you press the button, okay, when you press the button you complete the circuit. When you complete the circuit, it turns the electromagnet on. That will then pull the pivot towards the electromagnet, sometimes they call the pivot the armature, just means arm, like your arm pivots. Basically the magnet pulls something towards it. So it pulls something towards itself. It's normally like a metal pin or an arm or something like that. Anyway, when it does that, it does two things. First thing it does is it moves this arm here, so it pulls this arm into the strike position. So it's about to strike the bell, so it's like a little hammer. Okay, but it also breaks the circuit. which obviously turns off the electromagnet. And when the electromagnet is turned off, the next thing that happens is, so basically it pulls it towards it, that breaks the circuit. When the circuit's broken, the hammer is released. And strikes the bell. Okay. That diagram there is terrible, by the way. There's a much better one in your book, but the concept's sound. Okay, you've got a little pivot, so you press the button, it pulls something towards the electromagnet, which breaks the circuit because it's been moved out of its position in the circuit, and it puts the hammer into the strike position. Once the circuit's broken, it goes back to its normal position, and then that hits the bell. Okay. This concept's used in things like RCCD devices, residual charge couple device, which you do in electricity. So under your stairs or above your stairs or somewhere near your stairs, don't have to be wire, it's always near stairs, you'll find your electricity box. In your electricity box you'll have a load of boxes, they've got a switch on them, and sometimes they go up, and you'd say that's tripped, and you can put it back down. But what you're doing with those, what you're doing is you are resetting an electromagnet when you do that. Okay, so the whole point there is you have a circuit that's set up like this, and it's known as a circuit breaker, and you have an electromagnet here. Okay, now if the current gets too strong, so if the current gets too strong, then the magnet pulls this bit down towards it. If the current is okay, then the electromagnet's not powerful enough to pull it down towards it. But once it's pulled down towards it, you have to physically put it back into place. Okay, that's what you're doing when you put that switch back up. Okay, so it starts off like this in the red one. That's the start position. If the current is too big for the circuit that's designed for, the electromagnet then pulls the switch down, which then breaks the circuit. But it's physically broken, you have to then push it back up. This is different to the electric bell. The electric bell is designed so that when it breaks it goes back to its original position. It's got a bit more of a spring in it, so it springs back into position. And they're the two main uses. But what you want to be thinking about is you want to think about, electromagnet comes on, it breaks the circuit, that makes the electromagnet go back off, and then this happens. That's generally how we use them.